Okay, I think we can start. Hi everyone, thank you for joining us for the Physics Hour, a weekly event to explore different fields of research in physics and ask leading scientists some of your burning questions. My name is Julien Pierre, and we also have Simon here to help with the Q&A after the talk. Before we begin, many of us are likely to be turning in from different places, but I'm coming from Sherbrooke, which is situated on the territory of Wabanana-Cake and Endekina nations. I acknowledge the diverse indigenous group whose presence marks the territory from which I'm joining you today. And I invite everyone to learn more about the land that they live and learn on through the links that will be posted in the chat. So the Canadian Association of Physicists is the voice of Canadian physics, representing physicists in all parts of the career. The CAP provides leadership and support to the Canadian physics community by celebrating Canadian physics achievement, keeping members up to date, and by running various initiatives like the one you see below. The CAP Student Advisory Council was formed in 2019 to create a strong student voice within the CAP. We are egalitarian, diverse, inclusive, and action-oriented group which seeks to represent, support, and unify physics students across Canada. Some initiatives we're currently working on include advocating for increased student funding, advertising student opportunities through our website and social media, and interviewing physics students across Canada to understand how we can best serve the community. If you're interested in learning more about what we do, I encourage you to browse our website. We represent all physics students in Canada, so please get in touch with us through our email or social media and share your voice. Now, I'm pleased to welcome today's speaker, Renée Hložek.
Thank you so much. Really appreciate having this opportunity to speak to you. Je suis très heureux d'avoir la chance de parler avec vous et de répondre à des questions sur choses comme ça. So I'm going to share my screen with you. Fantastic. So I'm really excited to be able to tell you just a little bit about the questions that underpin my research, and then some of the ways we use observations to answer some of those questions. And I really love the fact that we are thinking about the lens that we're on. Of course, that's the same with telescopes. It's really important to consider where we build telescopes and how we engage with peoples on the land that those telescopes are situated. A lot of my work is using telescopes that are built in the Atacama Desert in northern Chile, because the sky is really clear there. So let's see. Oh, now what? There we go. So, you know, we sometimes think of astronomy as just, you know, beautiful stars in the sky. We look up, we see these incredible clusters of stars here. I like to show this because I'm from South Africa, and we have in the southern skies two satellite galaxies that you can see here, the Large and Small Magellanic Clouds, and they're orbiting our own Milky Way galaxy and interacting with our own galaxy. And that's just signs of the fact that even though the sky maybe looks like it is fixed, there's a lot going on, and there's a lot we can learn about the evolution of the universe just from observations. So I think of myself as someone who's presented with a puzzle. The universe is underlying all of the observations. There's a lot of simple mathematics, but we only get little pieces of information through our observations of the night sky at a time. And so we need to look and take those observations and try to piece back what the universe is made of and how it changes with time. So how do we do that? Well, I have to share this. This is an animated video that you can show your brothers and sisters at school. And the reason why I like leading with this is because, so this is the animator drew what they thought I looked like. So this is me as a cosmologist. But one of the things that we stress in that video is that underpinning a lot of what I do is Einstein's theory of general relativity. So Einstein's theory, which describes the interaction between what the universe contains, what it's made of, and how it changes. How does the topology change, and how does the evolution change? And even though people sometimes talk about relativity as being, you know, complicated theory, the equations are actually, there aren't that many of them, and in much of the universe, it's deterministic. So much of the universe, the way it's described through relativity is, in cosmology, is large scales, big galaxies, clusters of galaxies, and how everything behaves. And we have, you know, a handful of equations that then help us to decode all of that. And there's a great quote, which is that, you know, space tells matter how to move, and matter tells space how to curve. There's this relationship between the total stuff in the universe, and I keep saying stuff partly because we're used to thinking of mass in all of our physics classes. But of course, the theory of special relativity tells us that there's a relationship between the mass of something and the energy of something. And so when we talk about cosmology, we actually want to put you and me and photons on the same scale. And so instead of talking about the mass of stuff, we talk about the energy of stuff, because then I can compare the energy of radiation and the energy of baryons when I take the mass of baryons times mc squared, and I can actually compare them. So when I talk about stuff in the universe, I really mean energy in the universe. Okay, so I got a bit ahead of myself. What is the universe made of? The first piece of the pie, the cosmic pie in the universe, is baryons. I've said this word a couple of times already. So baryons you can think of as all the stuff we know and love. So you, me, my cat, the sun, all of the stuff that's made out of protons and electrons. And one of the key characteristics about baryons, and you can see here even in my apartment this afternoon, is that baryons interact with photons. They interact with light. The only reason that you can see me right now is that there is light bouncing off my face. And that light is what enables you to see my face. Now, that's a sort of fundamental principle of light. What we can do is we can relate the amount of light we see to the amount of stuff in the universe, right? The amount of stars, for example. So material that isn't reflecting light also makes its own light. And that will be important in a moment when we talk about stuff that doesn't reflect light. And so we can do a cosmic accounting, and we can say, let's look at all the stars that I see, all the planets I imagine there are, and let me add up how much of the universe is made of baryons. And when we do that through our calculations, we find that only a small fraction of the total energy in the universe is made of baryons. We cannot have more of the cosmic pie made out of stuff we know, because we can actually predict what that would do to the universe that we see. And so if we match the universe that we observe with our theory and our analysis, we estimate that about 5% of the total energy in the universe is made of baryons. Now that's quite stressful, because that 5% is everything we really understand. So it's Earth, it's neutrinos, it's stars, it's just gas in the universe, it's the Milky Way, it's all of that stuff. That's 5%. So the other, the rest of the pie, the other 95%, is stuff that we're learning about and trying to learn about. And the first part of this cosmic pie is called dark matter. And in fact, this is a term or a name that was derived from an astronomer called Fritz Zwicky. And you can see this characteristic photo. He was a very eccentric man. He wasn't a very nice person, but he came up with the term dark matter. And in fact, lots of pioneers, including Vera Rubin, studied the observational implications of dark matter. Now, what are they? One of the things that we find is we can take an image of a galaxy, and we can take the light from the galaxy and actually split it up into a spectrum, just like you do in physics classes. And because we can split that light up into a spectrum, we also can figure out what the galaxy contains, because we know the lines in the spectrum that correspond to elements, on Earth, hydrogen, helium, etc. And we can measure the spectrum of this galaxy at different places. And what we can do is we can actually measure how the galaxy is rotating. So we can measure, if it's turning towards us on one side and turning away from us on the other side. We can do this for tons of galaxies all over the place. We can measure their rotation curve. And what we find is that as we get further away from the center of the galaxy, we would expect that the speed of rotation, the velocity, decreases as you get out to the end. But what we find is that, in fact, it flattens out. So even on the outskirts of the galaxy is moving at the same pace as it is much further inside. It's rotating at that pace. And so that is confusing, because if you imagine there has to be something that's holding it together, otherwise it would just fling apart if it was rotating at such velocity. And this is one of the first pieces of evidence or hints that there was a thing called dark matter. And so initially dark matter was the term to describe this stuff that we couldn't see, that we knew had to be there because it was keeping galaxies intact. There's another really characteristic piece of evidence for dark matter that we see in the cosmos. Now, this is an image taken with the Hubble Space Telescope, and you'll see some really interesting things. You see some galaxies in the background that look kind of like normal galaxies, like spiral arms, etc. There are some galaxies in the foreground that are bright and orange or yellow and fuzzy, very big. And this in fact, all of the fuzzy yellow galaxies are in a cluster. They're all together, they're bound gravitationally. And then what you see are these kind of stripes sort of around, seemingly in a circle. And those are what we call the Einstein rings of this cluster. So what is happening here? Oh, I'm going to skip ahead a little bit and then hopefully show you that. But I'll come back to this slide very briefly before I tell you exactly what's happening and why we get those interesting arcs. We get them because of dark matter. And in fact, we can use calculations like how much of those arcs we see to tell us how much dark matter there is. And we find that in fact, there's 25% of the universe made up of dark matter. There's another 70% made up of dark energy, which I'll get to in a moment. The key thing here is that 95% of the universe is this mysterious stuff. Very different. Dark matter, dark energy are very different. And we'll learn a little bit more about them in the rest of this talk. So how do we measure dark matter? I just told you that it is causing those strange arcs, but let's think a little bit more about that because we want to measure the effects of dark matter so that we can figure out a little bit about what it is. I also told you at the beginning of this talk that you can see my face because I reflect light. So this image I really love is just a mirror in a building, and it's showing you how you can see the building because of its reflection. Now, if you had an infrared camera, or if anyone has been tested for COVID temperature with an infrared camera, you know that depending on the temperature that you give off infrared radiation. Now, we can't see it with our eyes. If we look at this picture of a giraffe, in visual light or optical light, it just looks, normal. It's the light rays are bouncing off the surface of the giraffe. But if we look in infrared, you can actually see the temperature of the giraffe in different places. And so you notice that the ears of the giraffe are significantly hotter than the rest of the face. And this is key because baryonic matter either reflects light or makes its own light. So if I measure a star, I can determine what the temperature of that star is if I can figure out through observations what is the distribution of light at various frequencies. So if you heat me up, I make more light at higher frequencies than at my current temperature. Now, dark matter doesn't do that. But I showed you that image before of the Abel cluster with these weird wibbly lines. So now let's use another analogy of being on Earth. If you take a candle, as you see in this image, and you take a wine glass, the bottom of a wine glass, you notice that as you change the angle of the lens, the bottom of the wine glass can act as a lens, and you can move the bottom of the wine glass into the line of sight of the candle flame. And depending on the angle of the lens, you get different shapes. And if you look here, if you can see my cursor, you see very similar ring-like structures to the ones you saw on the Abel cluster. So if we go back to that, very similar to these structures. They're not entirely, rings. There's some broken up pieces. But I see that this image of the galaxy has been distorted. So these patterns that you see here are images of the distant galaxy that has been distorted out into this ring-like filament structure by the matter in between us and the background galaxy. So if we add up the light that we get from these kind of orangey cluster galaxies in the middle, and we convert that to mass using the relationships like E equals mc squared, there's nowhere near enough mass to be doing this kind of distortion, to be making this kind of distortion pattern. And so that's a piece of evidence that we have that in fact, there's something we can't see that is doing the distorting of these background images. And that is what we call dark matter. So it's something that doesn't interact with light. It doesn't generate its own light. Light doesn't bounce off it, but it does distort the space-time around it so that the distant light from the background galaxy is distorted, much in the way that the candle flame light is distorted by the lens that you have. But I haven't told you what dark matter is. I've just told you what dark matter does. Now, myself and my group, we study a certain kind of dark matter called scalar field dark matter. Now, you might ask yourself, what is a scalar field? A scalar field is a concept that you don't really deal with that much as an undergraduate, and yet it's something that when we think about the Higgs boson, we have a little bit of an understanding of a field. And in fact, if you consider the temperature in this room, you have a scalar field. So it's a scalar because it has just one, it's specified by one number. It's not a vector. So it just has an amount, temperature is a number, but it's a field because the temperature can be described in 3D position in this room. I am near the vent of my air conditioning unit. And so the temperature around me is a little bit cooler than right next to the window. And so I can describe the temperature field in this room as a scalar field. Now, when I think about dark matter as a scalar field, I'm actually thinking of a cosmological scalar field, an object that has a density that is changes in the universe. And in fact, the scalar field also has a mass. The mass is very, very, very light. In fact, it's ultralight. What do I mean by ultralight? If I'm trying to measure things in kilograms, that would be the mass of a cat or the mass of a car. If I want to try and measure something, if I'm baking and I want to have very fine measurement, I change my scale and I turn it into grams because I want to measure something very, very precisely. When I get to very, very, very small masses, however, I would just have a ton of zeros in advance of my decimal point. And so I can actually switch to a different unit of measure. I can start to measure things directly in energy instead of measuring them in mass. And so I can convert kilograms to EV or EV over c squared. If I do that, then 1 electron volt, which is the unit of mass energy that we talk about, 1 EV is 10 to the minus 36 kilograms. Okay, the scalar fields that I study are much smaller than that. So a proton weighs 9 times 10 to the 8 EV. So roughly 1 billion EV is the mass of a proton. The axions that I study, these ultralight scalar fields, are 10 to the minus 22 EV. So if you think 1 EV is 10 to the minus 36 kilograms, and the mass of the scalar field that I study is 10 to the minus 22 EV. So it's something that has a tiny bit of mass, but we think the density or the mass, sort of as a function of space, can change all over the universe. And this is important because this scalar field can have, on the largest scales in the universe, it can actually have an impact on how the universe evolves with time. And we don't notice it on very small scales in this room because it's weakly interacting with light. But this axion can have profound implications for things like how different galaxies clump together. So at the moment, I am trying to figure out with my students and my group, what are the observational implications of this kind of dark matter as opposed to other kinds of dark matter that maybe you've even heard of? How does it change the way matter clumps together? How does it change the way the light is distributed in the sky if we look at the light from the Big Bang? And this is a fascinating area of study. Now, that's only one part of the dynamic duo of dark materials. So I mentioned that 25% of the universe is made of dark matter. I also mentioned that about 70% is made of dark energy. So how do we measure dark energy and what is it? Now, if dark matter is matter that doesn't interact with light, dark energy is something totally different. So the one main point I want you to get out of this talk today is that dark matter and dark energy are very different, even if we both have a lot of ignorance about them. We can think of dark energy essentially as a form of kind of anti-gravity. So dark matter, we know it behaves like ordinary matter, it just doesn't interact with light. Dark energy behaves completely different to anything we know of. And in fact, it sort of seems to be something that's pushing against gravity on the largest scales in the universe. So how do we measure dark energy? I love this photo. This photo was taken in Manhattan, in New York City, in the US, at the time of Hurricane Sandy, which was a big storm that knocked out all the power in the city. And in fact, all the streetlights in the city were gone. And so if you wanted to cross the road, you would have to use the brightness of the headlamps to tell you if there's a car. And I love this as a sort of illustration of that. But if you ask someone, how do you know that the brighter the headlamps are, the closer the car is to you? Most of the time, we just take it for granted. We do that calculation in our heads. We're not actually doing maths. We just intuitively know the difference. And what we're doing is we're applying the inverse square law of distance. The brightness of an object decreases as 1 over the distance squared from us. This is true in space as well. If we can find something, if we know how bright it is intrinsically, like the car headlamps, we can use how bright it appears to us to tell us how far away it is. And we do just that. We look at galaxies. This is the beautiful Whirlpool Galaxy. And if you concentrate on the little arrow, you can see that if I take, these images were taken before and after a very bright explosion in 2011 in the Whirlpool Galaxy. And this explosion is a type 1a supernova. These supernovae, a lot of them exploded when the dinosaurs were still on the Earth. So the light has been traveling from this exploded star to our eyes for many, many years. And those stars, of course, are no longer there. So we have some beautiful images of supernovae and galaxies. This is another one taken by the Hubble Space Telescope. And you can see this beautiful galaxy with a spiral arm, this dusty arm, and then the supernova is in the corner here. The reason why these supernovae are so useful is because they allow us to measure distances across the universe. And that tells us something about how the universe is changing. Because if I can measure, sort of if I have signposts to distances in the universe, then I can learn about what is the shape of the universe, what is the geometry of the universe. In order to do that with confidence, in order to measure across the universe how the distances in the universe are changing with time, because the universe is evolving, I need to develop large samples of these supernovae. In fact, the Nobel Prize in 2011 was awarded for this research. So it was 3 scientists who measured a small sample of these supernovae. And now we're pushing to measure hundreds of thousands of these objects. And the way we're doing that is with a telescope called the Reuben Observatory. Now, the Reuben Observatory is going to measure these objects in the night sky. And I want to play you a very short video about the Reuben Observatory because in Canada, we are pushing to have access to data from the Reuben Observatory. So we will be able to access some of these wonders. I should be able to play this. It's named after Vera Rubin, who was a pioneer in the study of dark matter.
The night sky, our window to the universe beyond. Immense, mysterious, powerful, quietly beautiful. Cosmic events at the edge of our imagination unfold in the darkness, ready to be discovered. When we look at the night sky, we see into the past. Untold stories carried through space by light, the great historian of the cosmos. Technology has evolved over centuries, allowing us to look farther, to the edge of our horizon. We invented telescopes to explore and cameras to capture these traveling messages. Yet the changing cosmos remains unseen. A new telescope opens its eye and captures it all, the objects that move and those that flash, even those we cannot see with our eyes. Every few nights, it covers the sky, finding all that has changed. And within minutes, new glimmers of activity are carried around the Earth to anyone waiting to explore them. What will you discover that no one has seen before? It's time to find out.
So the key point here about the Reuben Observatory is that it's going to measure the sky very many times. So roughly it can measure the whole sky every 3 days, which means it will be able to detect a lot more of these explosions that are happening from night 1 to night 2. If I scan the sky today and then I scan it in 3 days, I can take those images and subtract them and figure out what is new that has exploded that I didn't see before. And so we're going to find very many of these incredible explosions that tell us something about distances in the universe. So what do we do with all this data? So as part of my work, I do a lot of statistics. And the reason why we need to do statistics in cosmology is because instead of being an experiment that we can repeat many times, I actually have to only use the data that I can see and try and make inferences about what is going on. So if I think about all the supernovae that have been discovered so far, it's like saying I can model the whole universe just as this fish, right? Most of the supernovae that I have that are in existence right now that we've found, we've studied them very, very well and we understand them, and that's great. But now imagine I go deep sea diving and I see tons of fish. Some of the objects that I see, just like some of the stars that are exploding, aren't actually going to tell me about distances in the universe. They're going to just be stars that exploded. They're not going to be these beacons that we need. And so I need to use a lot of statistical methods to separate out these different populations of explosions, some that are useful as a distance indicator, as a lamppost, and others that just tell me about how stars die. And in order to do that, I need statistics. And in fact, I use the statistics of this guy. So this is the Reverend Bayes. Now, you may not have studied Bayesian statistics yet, but Bayes has developed statistical theories that basically take into account what I already know about the universe and how it informs the decisions I make. Now, what am I talking about? How can I use my prior knowledge of something to affect the future? Well, what if I asked you a question? If I told you that I got home from work today on a dragon, would you believe me? Now, if you only use the fact that I'm sitting here in my house, there's nothing about me sitting in my house that says I didn't come home via a dragon. the reason why you know I didn't is because you know dragons didn't exist. So in fact, we're always using our prior knowledge of the universe to inform how we understand the observations that we see. And the Reverend Bayes included this in a more formal way. Now, why am I talking about this at all? Well, when I look at all of these explosions and I'm trying to figure out which ones are going to tell me something about cosmology, just like if I looked at that huge picture with all the fish and I tried to pick out the ones of a certain type, I will have some confidence that I'm doing a good job in separating out these different objects into different types. And then I fold that in to all of my calculations about what the universe contains and how it evolves. So if I want to understand how much of the universe is made up of dark energy, for example, how much of the universe is dark matter, if the star here is the kind of correct answer, there's always some uncertainty based on my measurement error, based on my modeling, based on my theory. And so I have some uncertainty in the amount of the universe made up of either of these parameters. And if I have good Bayesian models, it basically will allow me to make my contours of uncertainty smaller and smaller by using all the data at my disposal. So to put everything together, I use observations from telescopes that are being built, that are in existence around the world. And I use those observations and theory and statistics to build the puzzle of the universe, to understand how we went from the beginning of the universe, when the universe was neutral gas, to when the first stars formed and galaxies, and to today that we can see. And it's important, as I think of all of this together, that I don't just have a theory, but I have a theory and I have observations and I have statistics to bring it all together. And that's why I think cosmology is fascinating, because it allows us to ask these big questions and to answer them quantitatively. But you already know that there's a ton of stuff in this model that we don't understand. I've mainly posed more questions than answers to you. And so I hope that some of you will be interested in thinking more deeply about this and doing research in cosmology and thinking about projects, because there's a ton of interesting questions to answer, and there's a lot of really fun work to do. And so I hope some of you will be inspired by this and think of some projects that you would like to work on in cosmology. I want to just close, because I know we're going to have a little bit of discussion now, but I want to also add some things that I wish some people had told me when I was an undergrad researcher in physics, just very briefly at the end. I think one of the things that's scary when you start doing physics, particularly when you start doing research, is it seems that everything is scary and impossible. But learning the difference between things that are scary but they are doable and things that are undoable is really important, because they will help you gain confidence in asking questions and answering them yourself. I always say that that confidence to try something before you are 100% certain it will work is what separates us from doing problems in our physics classes where we know all the answers are in the back of some book, right? From research where you don't know the answer and your professor doesn't know the answer, and you're trying to build an intuition about whether something is right or not. In order to do that, you need to question everything you do, not in criticizing yourself, but ask, if I come up with this answer, is this as big as I expected it to be? Is it smaller? Is it larger? What is the next outcome of the thing I've just learned? Because if I start doing that logical thinking, it will help me debug mistakes that I might make. I hope that you will ask me lots of questions, because asking lots of questions is really important. And in fact, it's a skill that you can learn. And I think that doing research and doing physics, it's fun because I really enjoy it, but it's really important to treat learning like a job. If you respect it, you, instead of thinking that, oh, I'm going to only rush and do everything at the last minute and make my life difficult, if I start to think of this as a job, and also that I am not, I respect my professors, but also that I am part of this whole process, and I am also a learner. So it doesn't mean that my professors only have all the say always, that you can also advocate for yourself. And then finally, don't let anyone make you feel like you don't belong in the career and that you shouldn't be asking questions, because this is why we do it. We ask questions, we learn. That's the whole point of this. And anyone who tells you otherwise isn't being a good physicist. I hope you have lots of questions for me. I'll leave you with the slide of the puzzle, and I'll take questions now. Thank you.
Thank you so much, Professor Hložek, for this very interesting talk on cosmology. Before I end the recording and we can move on to the Q&A, I'll invite everyone to register for our next talk happening next week, which will be delivered by Professor Ben Yuling from the University of New Brunswick on magnetic resonance imaging in material science. So I'll end the recording now.